Hello guys, let's continue GR paper 0177 from problem number 31. In this video we have solved up to 30 problems in our previous videos. Problem 31 is positronium as an atom formed by an electron and positron anti-electron. It is similar to the hydrogen atom with the positron replacing proton. A positronium atom make a transition from state n is equal to 3 to state n is equal to 1. The energy of photon emitted in this transition is close to. Guys, we have an atom. This is the nucleus and these are the shells of this atom, but in this case a nucleus, there is a positron electron with positive charge instead of proton, and electron revolving in the third shell will jump to the first shell. We have to find the energy emitted in this transition when this electron jump from n is equal to 3 to n is equal to 1. This is n equal to 3, this is n1. In this case, this atom is similar to the hydrogen atom, but the difference is that there is positron, an electron with positive charge instead of proton. So the ground state energy by Bohr is given by E is equal to 2 pi square m e power 4 divided by n square h square. This is the ground state energy calculated by Bohr. Here n is the shell. If n is equal to 1, then this is the ground state energy E1. Its value is always equal to 13.6 electron volt when we have hydrogen atom. But in our case, in this atom the proton is replaced by positron, so this is a two-body system and we have to deal with it as a single body. Then we will calculate the reduced mass for these two bodies to make it a single body, to treat as a single body with it. For this, the reduced mass is equal to m1 m2 divided by m1 plus m2. Here m1 and m2 is the mass of electron and positron. Because these two particles have same mass, then we can say that m divided by m plus m. This is equal to m divided by 2. So the reduced mass of this system will be half of the mass of electron. So this reduced mass formula will little change this energy formula. We can see that if we put here the reduced mass, and the value of reduced mass is m by 2, so this will become half of 2 pi square m e power 4 divided by n square h square. In fact, it will reduce the energy, ground state energy of electron to its half. So the ground state energy of electron in positronium atom will be 6.8 electron volt. This is the ground state energy and its symbol will be minus. Now we will calculate the energy in this transition when this electron jump from n3 is equal to n1. For this E, this is equal to, if we put here, this is constant, this is all is constant, En, this is equal to minus E1 divided by n square. Now if we are finding the energy, transition energy, then it must be the difference of n1 E1 divided by n1, and this must be n3. We will take common E1, then 1 over n3 minus 1 over n1. This is a square, so En, this will be something like that. Now we have to calculate this energy value numerically. Then En, this is equal to E1, this is minus 6.8, N2 1 divided by N1 is 3 square minus N2, this is equal to 1 square. The electron is going from 3 to 1, so if we calculate this, then it will result minus 6.8 into 1 over 9 minus 1, this will result 6.04 electron volt. This is the energy which will radiate this positronium atom when its electron will jump from N3 to N1 in this positronium atom. So this is close to the option A, which is 6 electron volt. So option A is our right option. Next problem is 32. If the total energy of a particle of mass m is equal to twice its rest energy, then the magnitude of the particle relativistic momentum is. Here we have to find the relativistic momentum of a particle having mass m and total energy twice its rest energy. Rest energy is always, this is equal to mc square. This is the rest energy, m naught c square. This is the rest energy of the particle. Now we have to calculate the momentum, relativistic momentum, if this is the rest energy, and in our case the rest energy, the energy is twice of rest energy. So the total energy is twice of rest energy, and rest energy is m naught c square. We have to find relativistic momentum of this particle. The formula for total energy, this is equal to E square, this is equal to m naught square c power 4 plus p square c square. This is the formula for total energy of a relativistic particle. Now it is given that the total energy is 2 m naught c square, so we will put here m naught c square whole square. This will equal to m naught square c power 4 plus p square c square. This will become 4 m naught square c4. Transfer this term to this side, it will become m naught square c power 4, this equal to p square c square. This will become 3 m naught square c4, this is equal to p square c square. C square will cancel out this with the 2 with the c square, and it will become c square. Taking square root of the both side, it will result p this equal to square root 3, and this square will cancel with square root, so square root 3 m naught c. So this will be the relativistic momentum of that particle. If its total energy is twice its rest energy, then this option is option D. So option D is the right option in this problem. Next problem is 33. If a charge pion that decays in 10 power minus 8 seconds in its own rest frame is to travel 30 meters in laboratory before decaying, the pion speed must be most nearly. We have a pion which have 10 power minus 8 second time in its rest frame to decay. It travel in laboratory 30 meters before decaying. We have to find its speed. Formula for speed, this is equal to V is equal to S over T. Here S is length, this is a distance. We denote here it is L, and T is the time taken for this distance to cover. Here the process in his laboratory frame, then it must be equal to L prime divided by delta T or L divided by delta T prime. We will use either formula for length contraction or time dilations, which will include the gamma term which is equal to 1 minus v over v square over c square square root. So in this formula we are using a term for the contraction of length. We will use here L, contract time. L is equal to, this is equal to L into 1 minus v square over c square square root. We will use this term in this formula because it is in laboratory frame. We are putting here that v, this is equal to L divided by delta t into 1 minus v square over c square. We have to find this v. We will find out v in this formula, then squaring both sides we will get v square, this is equal to L square divided by del t square into 1 minus v square over c square. For multiplied this term, this will goes v L square del t square minus L square v square divided by del t square c square equal to v square. Rearrange this here, v square plus L square v square divided by del t square c square, this is equal to L square del t square. Take common v square and to 1 plus L square divided by del t square c square. Now it is equal to L square divided by del t square. Taking LCM, that v square and to del t square c square plus L square divided by del t square c square, this is equal to L square del t square. Del t square will cancel out with this del t square, so the formula will become, this is v square, this is equal to c square L square divided by del t square c square plus L square. This will be our formula. Now this v square, this is equal to c square L square divided by del t square c square plus L square. We can write L square divided by del t square c square plus L square and to c square equal to v square. Putting all values, L is equal to 30, t is equal to 10 power minus 8, this is equal to 30 square divided by t is 3 multiplied by 10 power minus 8 square multiplied by this is c, this is equal to 10 power minus 8 square plus this is 30 square whole into c square, this is equal to v square. This will become here, this will become 900 divided by, this will become 909 c square. We are taking here v square, this is equal to 100 divided by 101 c square. Taking square root of both sides, we will get v is equal to 100 divided by 101 square root into c. Calculating this will become approximately 0.99 c. Multiplying this with speed of light, we will get this answer. So option C is the right option in this problem. Next problem is 34. In an inertial reference frame S, two events occur on x-axis separated in time by delta t and space by del x. In another inertial reference frame S prime moving in x direction relative to S, the two events could occur at the same time under which if any of the following condition. We have two events, an inertial frame S and inertial frame S prime. occur at the same time, we have to find the right condition for all these. Now we have to find the right condition. For space separation, we have a formula del S. This is equal to del X plus del Y plus del Z minus C del T. This is a formula for space for two events when they are separated in space in time. Now we have, in this case, we have, there is only x separation in the x direction in space, then this will formula will reduce to del x minus C del T. This is the separation formula in our case. Because these two are 0, there is no separation in x and y direction, the separation is only in x direction, so formula reduced to this. Now we have three conditions. One, time likely events, space likely events, and light likely events. There are three conditions: time likely, space likely, and event likely events. When delta is less than 0, for this condition, the very first condition, delta S is always less than 0 for time likely events. In this, there is separation in time, but the space is same, means there is no separation in space. Del X is 0 and there is only time separation, so del S will give minus value, negative value, so this value will be always less than 0. For space likely separation, delta S must always greater than 0, because in this there is no time separation, only space separation, so this term will goes to 0. In light likely events, there is no separation in space and time, so delta S will 0. In our condition, there is the same time under the two events occur at the same time, means there is no time separation, there is a space separation, so delta S always greater than 0. For this we will find the condition that the delta S, for this delta S will greater than 0. If delta is greater than 0, then this total term delta X minus C delta T, this will be greater than 0. If we find the value of C here, so delta X greater than C delta T implies that delta X delta X divided by delta T, this will always greater than 0. So this is the right condition for this for these two events to occur when they are same in the time. Delta X divided by delta T always greater than 0. So this option is greater than C. This option is right in C, option C. So our option C is the right option in this problem. Next problem is 35. If the absolute temperature of a black body radiation increased by a factor of 3, the energy radiated per second per unit area does which of the following? This is a black body radiation. The energy density of the black body, this is given by Stephen Boltzmann law. This is sigma T power 4. This is the absolute temperature of black body. If it is increased by factor of 3, the absolute temperature is increased by a factor of 3, then the energy density will increased. So we will put here sigma into 3T whole power 4. This will be equal to 81 sigma U prime. This will be equal to 81 sigma T power 4. This is equal to 81 multiplied by U. Then the new energy density will be 81 time increased by the initial one. So this is decreased by 81. This is wrong. this is wrong. 927. So energy is increased by a factor of 81, and if absolute temperature is increased by 3 times. So this is the last problem of this video. Please share, like and subscribe.